Boom. Hello and welcome back to Calculus 2, section 8.6, alternating series. So this is the last one we are covering. There are more tests than this, not just 10. There are more.
Quick favor.
Yeah.
I believe I left my wireless mouse in 351. If you have the key, could you just... Okay.
Security.
Their desk is closed. The one down by the...
No, they're always open.
Where is it? Did I go to the wrong one?
By SO12.
Okay, thank you.
Hello and welcome back to Calculus 2. What? Section 8.6 alternating series. I don't remember where I stopped. So this is the last one out of 10. There are more than 10 tests in mathematics, but we are covering 10 in Calc 2. So alternating series is very easy to spot because alternating series has, let's say 1 to infinity, it has this alternating term, -1 to the n, and then some kind of sequence after that. So what is this -1 to the n? It gives us each term, right? It goes 1, -1, 1, -1, 1, -1. So when you start plotting, 1 point goes below, 1 above, 1 below, 1 above, right? So it goes like that. It alternates the side of the n line, therefore alternating series. We can just look at -1 to the n of n from 1 to infinity. So when n is equal to 1, you have first term to be -1 plus, and then when n is equal to 2, which is the next term, -1 squared is +1, so this becomes 2, and then -3, and then +4. No. Yeah, +4, -5, +6, -7, +8, minus da. It goes forever. And you see that signs alternate all the time. So, as I mentioned, right, it is very easy to spot alternating series because they all have this term. However, this term can be present in disguise, all right? And that would be cosine and pi. You see, cosine and pi is actually this. Is it? Well, think about the cosine and the pi. Here's your cosine and pi graph. This is where pi is. This is where 2 pi is. This is where 3 pi is. This is where 4 pi is. So what happens? You have at n equal to 0, you have 0 pi, cosine of 0 is 1. Well, -1 to the 0 is 1. Right? So they both start their sequence with 1. Then the next term is n is equal to 1, so cosine of pi is -1. And when n is equal to 1, -1 to the 1 is -1. So you see, they match perfectly. So you have to be careful. You have to be careful. If you see cosine and pi, it's alternating series. And obviously there is one for sine. Sine of n pi over 2 does the same thing. Right? Is this one shifted? The first one is positive. When n is equal to 0. When n is equal to 1. So we need +1, right? So when n is equal to 0, you get 1. Yeah, so that's it. So sine n pi over 2 is equal to the, and this is still alternating. Still alternating. You can have n plus whatever up there. It still alternates. So I will start this with mentioning that alternating series have -1 to the n, or cosine n pi, or sine n pi over 2. Yeah, I'm going to do a better job then. N pi over 2. There we go. So those are the alternating pieces. Now, the theorem for alternating series goes like this. If an is decreasing and limit an equals 0, all right, we have convergence. Further, and this is the big part right here, further, if, in addition, summation of an, when you take the alternating term out, converges, we have absolute convergence. Otherwise, we have conditional convergence. And I put CC for that one, and AC, absolute convergence, for that one. All right, this is way too many words. How about some diagrams? We start with some kind of alternating series, and we consider an. Consider an, and we get two branches now. This is a convergence branch, and this could be, this is a divergence branch, but in some bizarre cases it could still converge. So I am tempted to put divergence, but I kind of don't want to. So we can say unknown, X files. Can do that. So there are cases where if the conditions of decreasing and the limit an equals 0, if they both pass, you have the convergence. If they fail, it could still converge in some cases, but most of the time it's divergent. I kind of want to write divergent on this, but sometimes converges. Maybe I'll write that. There we go. Then we consider summation of an without alternating part. That can either converge or diverge, which would give you absolute convergence or conditional convergence. So now you have, instead of converge diverge, you have absolute converge, conditional converge, and diverge. But this is the tree diagram, like a path that you take. You get a problem, you focus only on an to see whether you go into converge or diverge track. And then if you're on a converge track, you solve the summation of an with whatever other 9 tests you know. And that can either converge or diverge. If it converges, then you are on the convergence branch, and you have another convergence. So two converge in a row, you have absolute convergence. If summation of an diverges, then you are on a convergence branch, but summation of an diverged, then we call that conditional convergence. And I'm going to give you an example to explain that in a detail. So let's take a look at first example, summation of -1 to the n over n squared plus 3 from 1 to infinity. So we consider an, which is 1 over n squared plus 3. And if you look at this, right, it's n squared, 1 over n squared plus 3. So this is like 1 over n squared. You know that 1 over n squared graphs this way for the continuous world, so the dots have to do the same thing in the discrete world. You see that it's decreasing, and you also know that the limit will go to 0. So let's go. Is it decreasing? Well, show that an plus 1 is smaller than an. That's the way to show decreasing. Next term is smaller. Or make the continuous analog, take the derivative. Is the derivative negative? Yes, it is. Great. Decreasing. So, but the, non-calculus way would be just to show this. So you show that 1 over n plus 1 squared plus 3 is smaller than 1 over n squared plus 3. And when you cross multiply, you get n squared plus 3 less than, this is n squared plus n plus 4. Right, when you FOIL it. When you cross multiply FOIL, you get this. Minus n squared on both sides. And you have that 3 is less than n plus 4. Now, remember that n is bigger than 0, right? So this holds for all positive n. That's correct. So is it decreasing? Yes, it is. What's the limit as n goes to infinity of 1 over n squared plus 3?
Over n squared plus n plus 4, that's not 2n.
Oh, it's a plus 2n. Yeah, you're right. Plus 2n. Plus 2n. So 2n. It's 2n plus 4. And you have the limit goes to 0. Both conditions are satisfied. That means that you are merging into a convergence branch. So on your path here, we pass this much, and we are up to, let's check, summation of 1 over n squared plus 3. So we are already on convergence branch. Now check summation of 1 over n squared plus 3. Now, I'm going to skip the work for this. This is the previous section. I'll just say converges by comparison test. Limit. Yeah, I'll write it out. So converges by limit comp test. So now we have the answer. Since an is decreasing and limit an equals 0 as n goes to infinity, and since summation of an converges, series summation -1 to the n divided by n squared plus 3 absolutely converges. Or converges absolutely, whatever you want to word. So we only look at an. If it's decreasing and the limit is 0, you hop on a convergence branch. And then you consider summation of that an by using one of the 9 tests. Maybe integral, maybe p-series, maybe telescoping, maybe whatever. This one was limit. And you have your absolutely convergent. Now, this absolutely converging is actually the convergence we had so far. If you say absolutely convergent for telescoping series, you are saying the right things. If you go within the p-series, you say absolutely convergent, still okay. So any of the previous 9 tests, convergence is absolute convergence. But we didn't have to specify that. So we just said converges, converges, converges. But the absolute convergence from alternating series is the convergence for all other series. So if you call them all, in all 10 tests, absolute convergence, you're fine. Conditional convergence is a new creature. That one we don't have in any of the previous tests. So again, absolute convergence is the equivalent to all of the convergence that you had in previous 9 tests. Conditional convergence is a new animal. So let's consider alternating harmonic series. So this is called alternating harmonic series. That's a, if you want to write it out to see, what it looks like, you will have -1 plus 1/2 minus 1/3 plus 1/4 minus 1/5 plus ... Now we know that if all of these signs are positive, you have harmonic series and you have divergence by p-series, integral test, whatever you want. Now let's take a look at alternating ones. We know that an is 1/n. Is it decreasing? Sure. And the limit 1/n is 0. So it passes both conditions. It passes both conditions. What does that mean? What does it mean? It jumps on the convergence branch, right? And then we consider summation of 1/n, which diverges by p-series or integral test, whatever. So in the answer, since an is decreasing and limit n goes to infinity of an equals to 0, and since summation 1/n diverges, series summation -1 to the n over n converges conditionally. How crazy is this? Harmonic series diverges. Alternating harmonic series converges conditionally. Yay! So, harmonic series, vanilla, right? Harmonic series diverges, and you pick either integral test or the other one. But alternating harmonic series converges. And we say converges conditionally. Now let's understand real quick. You have a question? Yeah, what does it mean converges conditionally? You see, you say summation of 1 over n diverges by p series. And we are all familiar with that. Summation negative 1 to the n over n converges conditionally. What's the difference between these two? What is the condition under which it will converge? Condition is to be alternating. That's the condition, to have that. You take it out, it diverges. You put it back in, it converges. You take it out, it diverges. Put it back in, it converges. You see that? Conditional convergence means that if you take a divergent series and you add alternation to it, it converges. That's what that's conditional convergence. Very good. Excellent. Alternation makes the series, makes the sequence jump up and down from the x-axis, right? N-axis in this case. And when you start adding those terms, they add differently than if you are adding the terms. So consider this. It's 1 plus half plus third plus quarter. So it's plus, 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 plus. And even though this is diminishing, it is not diminishing fast enough to add to a finite value. So 1 over n diverges. But this one over here is negative 1 plus half minus a third plus a quarter minus a fifth. So you see that it's adding a lot of negative terms. And that is enough to bring it over the edge of divergence, to push it down and kind of ground it and have it converge. So one more time, every single convergence that we had in the first 9 tests is actually absolute convergence. And absolute convergence from alternating series is at the same level of convergence. When it absolutely converges in alternating series, it's just convergence. But we have a new creature of conditional convergence. When you say that the series converges conditionally, that means it converges only because alternating term is there. And you can actually see that in the tree. You see that? If you remove the condition of alternation, it diverges. Bring that in, it converges. So we call that conditional convergence. If the alternation is there, it converges. If you take it away, if you take that condition out, it becomes divergent. And that concludes chapter 8. Now you might say, well, did we learn anything new in 8.6? Actually, you are learning the concept of conditional convergence. There is no new test here, because this part where you distinguish between conditional and absolute convergence is actually testing this. And that part, you are using one of the previous 9 tests. So I'm going to actually point with red into this and say, use one of the other 9 tests, because that's actually what solves it. So one of the 9 tests will give you either this or that, and then you have absolute or conditional. That's it. So you should study the tree and understand the tree, where you start from the problem, 2 conditions which are listed on your sheet. Look at the alternating series, number 6, I believe, or whatever. It will pass those 2. You hop on a convergence branch, use one of the 9 tests, whatever you have to, jump on one of these two branches. So study that. Ta-da! Chapter 8 is over. Next class on Monday. So we have Monday class, no Wednesday class. Monday class will be power series. So we are going to work on 9.1 and maybe 9.1. And then hopefully some lab time, right? Because you need to put the stuff together. See you Monday. Yeah, stupid Thanksgiving.